Swayam Prabha. Digital India. Educated India.
All right. So the overview of this lecture is that I'll give you some introduction and then talk about register allocation using usage counts, which is the simplest way of doing register allocation. Then I will talk about the conventional graph coloring based global register allocation. Then I will also talk about a simple local register allocation and how that could be extended for a global allocation with some amount of approximation. And maybe quickly talk about how register allocation is done in recent times. Right? What is the context? The context is that we are talking about the back end of the compiler. In yesterday's lecture, I think Professor Krishna Nandivada would have covered more about machine-independent optimizations. He would have talked about basic blocks. He would have talked about how to do certain optimizations within a basic block and possibly even across basic blocks, right? To do certain machine-independent optimizations. In particular, he would have touched upon terms like basic blocks, right? Instructions in a basic block, right? That's really what we need to kind of keep in our mind when we talk about it. So after you do this machine independent optimization, you actually go to the code generation phase where you generate code for a specific target machine. So if you're talking about, let's say, your x86 processor, then there is a code generation for the x86 processor. If you're talking about a RISC-V machine, then you are going to do code generation for a RISC-V machine. I think Dr. Krishnan is going to come back and sometime next week, and he's going to spend time talking about code generation. And a part of the code generation also involves instruction selection. So those things are going to be talked about later, right? What we are going to focus today is that after the code is generated for a particular target machine, how do we really do register allocation? Because code generation might be assuming what are called logical registers or temporaries. With that, they would have actually generated the code. And then you have to now say that, okay, in this particular machine, we know that there are 32 registers, etc. And therefore, we have to make use of only 32 registers and allocate them for program variables, etc., etc. So how do we do that, right? That's essentially what is register allocation. I'll talk about the exact, talk about the exact problem and how we go by that. Sorry. Another related problem to this is instruction scheduling, where we are going to talk about how to reorder instructions, either to avoid possible pipeline stalls or to expose instruction level parallelism so that processors can exploit that. These two topics, register allocation and instruction scheduling, and the optimizations that we do there, they are also related to each other. One affects the performance of the other. Unfortunately, we may not have a lot of time to talk about it, but I will at least allude to that problem that we may face and what kind of solutions can possibly have. So what we are going to focus in today's lectures is mostly about register allocation and to a certain extent about instruction scheduling. Why is this interesting, right? Almost all of the problems that we talk about in the back end of the compiler, they are very interesting and they are very challenging in the sense that the code that we want to generate, you want to generate an efficient code, and you also want to generate it in an efficient way. The code generator itself has to be fast. And unfortunately, many of these problems, like for example, whether it is the problem of generating the optimal code or the problem of doing optimal register allocation or the problem of optimal instruction scheduling, if you look at any of these problems, they fall under this broad category of NP-complete problems. That means that if you want to get the optimal solutions, you have to spend a very long amount of time, exponentially large amount of times. That's not possible. So you have to come up with efficient heuristics which can do this in a reasonably good way, but very, very fast, right? So all of these problems are NP-complete, like optimal code generation, register allocation, instruction scheduling. And if you want to combine instruction scheduling and register allocation, that's also complex and so on. So this is the context and this is the challenge that we are facing. Let's now look at the register allocation problem per se, define what the problem is, and then talk about what solutions we can have. Okay. So the register allocation problem itself, although we call it by the name register allocation, has two problems put together. One problem is what is called the register allocation, which is identifying which variables in your program and which temporaries in your program should be allocated registers. And also, when you say which variables have to be allocated registers, you also want to find out which variables can share the same register, right? And you can do this either in a global sense, meaning across basic blocks, or in a local sense, which is meaning within a basic block, right? And in order for you to have an efficient code, you have to do this register allocation in a global sense. That is when it would be more beneficial, because if you do it locally on a per basic block, you will generate code, you will actually use some of the registers, but that would be suboptimal, because at the end of each basic block, you will do certain spills and you will do certain reloads, which may be unnecessary. Therefore, you would try to do this in a global basis. Okay, so the problem of register allocation itself only tries to identify which variables can reside in registers and which variables can share the same register. That's essentially what is the problem of register allocation. The problem of register assignment is essentially saying that once you have decided which variables should reside in the register, what register can they use, right? And of course, once you have decided which variables can share the same register, what register can they share, right? This problem is somewhat trivial in RISC machines where all the registers are homogeneous. By that, what I mean is that you could actually use any one of the registers for that purpose. R1 is similar to R5, R5 is similar to R16 or whatever, except of course we saw that in some cases there is an R0 register or an X0 register which is hardwired to 0, which means that that register cannot be used for anything else, but all the other registers are identical. Whereas in some other architecture, particularly in CISC architectures and in DSP architectures, certain registers have certain importance. For example, there are the segment registers which are used for certain purposes. There are these accumulator registers which are used for certain purposes. DSP uses other complex registers which are used for certain purposes, where the assignment problem also becomes an important problem. In this talk, we will not talk so much about the assignment problem. We will actually assume that all registers are homogeneous, and then once you decide they have to reside in some registers, you can use any one of the registers. So we are essentially going to focus only on the register allocation problem, finding out which registers should reside in memory, which variables should reside in registers and which variables should reside in memory. Of course, when you are talking about RISC machines and RISC architectures, if you want to perform some operations, then arithmetic operations like arithmetic instructions can only have register operands. So eventually they may have to be brought into registers, but then if you have not allocated a register permanently for a variable or a temporary, then if it is a RISC machine and you have to perform some operations on that variable, then you will temporarily bring into some registers, perform the operation and put it back into memory. That is how you will deal with it, right? Not that you can access it directly from the memory and then perform the operation on it, because in RISC machines, you can't have memory operands. So you have to bring it into register. Maybe you will have some number of registers which are used as temporary registers, where they will be brought in, you perform the operation, again put it back into memory. Why is register allocation important? Why are we talking about registers per se, right? If your operands are in memory and you have to access it from the memory all the time, then you will incur a large amount of cycles to access them, right? Even if you have caches, it is still, right? It takes a few cycles to do it. Whereas register accesses are even faster, right? Register accesses are sub-cycles, right? And if it is there in memory, then you have to, and if it is a RISC machine, you have to move it into register and then perform the operation. So that already incurs one load operation and then a store, right? So variables which are in registers can be accessed faster compared to variables which are in memory. And that is why register allocation becomes important. Those variables which you access more frequently, you want to keep them in registers so that you would incur less amount of time executing that particular program. Okay, that already brings in the concept of doing register allocation based on usage counts, how often a variable is being used, right? Okay. So now to pose this register allocation problem, what we want to start off with that we have this intermediate, so we not even say intermediate language program, you can even think of this as the machine code generated program. So essentially you have an assembly program or assembly language program for the target machine, which has all your variables, temporaries, and so on and so forth, or maybe using temporary registers, whatever it is. It's actually a sequence of instructions that you have. And you also have the control flow graph, because you know the basic blocks, you know the control flow graph, and you know that your target architecture has k registers. Then the register allocation problem is essentially identifying, okay, which program variables must be allocated to registers, and which program variables can share the same register, such that conflicting variables are not assigned the same register. If the two variables are non-conflicting, then they can possibly share the same register, right? And among the set of variables and temporaries that you have, which one should be allocated these k registers, such that, right, you minimize the number of spill loads and stores that you would incur. And program you use at most k registers, right? So some of these variables are assigned to these registers, other variables are accessed from memory and then written back into memory. You can share the same register for two variables, provided they are not conflicting with each other. I will tell you what this conflicting is in a little later on, right? So this is essentially the problem, right, that we are going to talk about. And as I mentioned, this is an NP-complete problem, so you have to use heuristics to do this. And the heuristic could be based on simple usage counts, or could be based on this global graph coloring algorithm, which is Saiten's algorithm, or it could be other kinds of approximations like the linear scan allocator and so on. Okay, now let's just set the context for this discussion. So what are conflicting variables, right? We say two variables are conflicting if they are live at the same time. And what does it mean to say live? Intuitively, we say a variable is live in a particular program if that variable's value is needed somewhere below, somewhere at a later point in time, right? Somewhere in the future. When a variable's value is needed somewhere later in future, it means that we have to preserve that variable. You can't throw that away, right? So that is when you say that the variable is live. Okay, here is a formal definition of liveness. Again, you will come to this definition in a later discussion on data flow analysis, right? But let me just try to give you a very quick intuitive idea of what this is all about. Now look at this variable v, which is going to be used in a program point s, correct? And this variable in this particular control flow path was defined in this location in your program, right? So v was defined here, it was assigned a value at this point in your program, and was subsequently used in this point in your program. The question is v live in program location p? Should the value of v be kept carefully, right, when you are executing program location p? Right? We can't discard the value of p because the value of p is going to be used subsequently, and there is no other definition of v in this path from p to s, correct? Therefore, I can't discard this value. If there had been a definition somewhere here, I could say that, okay, this value of v may not be needed because I'm going to define it again later. But from this path p to s on all these paths, right, there is no definition of v, right? Therefore, at this particular program point p, the variable v is live. It doesn't matter if there are other paths to v, right? You still need to preserve the value of v in program point p, because right? There is an execution from P to S. There is a path from P to S in which V is being used, and there is no definition on that. Therefore, at program point P, the variable V is live. So when you talk about allocating a register, you say that you try to actually allocate a register and keep the value in that particular register, and you can't just take that register away at this program point P, because if you take that register away and you write something else into that register, then the value of V is lost, and therefore it cannot be used at this point in time. Of course, before you do that, you have to write this value into memory and then again possibly reload it. That is also fine, but then the purpose of keeping it in the register is lost. So what we are going to say is that once a variable V is allocated to a register, then preferably you have to keep it in that register wherever it is live, right? That's the idea. So if two variables are live at the same point in time, then obviously they cannot share the same register, right? If two variables are live in any point in program, then obviously they cannot share the same register. And conversely, if two variables, right, do not conflict with each other, that means that they are not live at the same point in any place in your program, they are non-conflicting, then they can share the same register. That's the idea. Again, you will see the notion of liveness in a much more formal way when I think Professor Uday Ketkar comes and then talks about data flow analysis. Okay, let's try to give some examples of liveness. Okay, here is a simple sequence of instructions, and here I am using all these temporaries S1, S2, S3, and so on. You can see that S1 is getting defined in instruction A, being used in instruction B, and that's possibly the last use for that. So if you look at the variable, it is live from instruction A to instruction B. Similarly, the variable S2 is live from instruction B all the way up to instruction D, and so on, right? This is the range where the variable is live, okay? This is the live variable, the range of this, live range of this variable, okay? So just to say here, the live range of the variable V, right, is from the place where it is defined till its last use. For example, if I take the variable S2, it is defined in instruction B, it is used in instruction C, but its last use is in instruction D, right? Instruction E does not use S2, therefore its live range starts from B and ends in D, right? This is one way of looking at it. There is also a convention where people say that it starts from the definition point and up to, but not including the last use point. So that definition is over here. For example, what I say here is it's defined, right, in program instruction B, and its use is till this particular point, even though it is used in this instruction, right? We are not including it because, let us say, if S2 is in a register R1, then that same register can also be used for S4 because S1's liveness ends at this point in time. So after you have read the value of S2, computed the operation, you can actually use the same register to store the destination. Remember when we talked about 3-address code, I said that for an instruction, the destination register can possibly be same as the source register. When it is possibly same as the source register, it only means that is the last use for that source register. In subsequent instructions, that particular source register is not going to be used, and therefore you can actually reassign it to the same register, right? Let me spend the next 2 minutes before I give a break for you, right, on these things, and take an example where we talk about this live variables across basic blocks, right? What we saw in the previous example is within a basic block, that is simple sequence of instructions. Here we have some kind of a control flow, okay? Again, let's not focus on too many things. Look at the control flow graph, which basically there is a condition evaluation. If the condition is true, you go this way. Condition is false, you go through the other way. And these are basically the statements executed in these basic blocks, right? Now let's look at the variables S1 and S2 here, right? Now, the question is variable S1 live at program point where S2 is getting defined? Sorry, let me just go back, right? Now you can see that this variable S1 is defined here. And if you go through this particular basic block, this is its last use. And if you go through this particular basic block, it is its last use. So obviously at this point in program, because this is the last use of S1, S1 is no longer needed here. So S1 is not live there. Similarly, if you look at this one, here also S1 is not live. If you look at the variable S2, S2 is getting defined here and is live and is going to be used across this particular basic block, right, in basic block B4. Similarly, S2 was defined in basic block B2 and is going to be used in here. Now, how do the live range of these variables look like, right? So you can see here, right, S2's live range starts from here and goes up to here. Then there is a hole which essentially represents this region over here, right, where S1 is not live, correct? And S1 is not live subsequently in the program also. But because of these control flow graphs and these control flow and these basic blocks need to be put in some order, you see that there is a hole here. And then in this particular basic block, S1 is live again from the beginning, from the beginning of this basic block up to this point. So that is being represented by this interval over here. Similarly, if you look at S2, S2 is live from the last instruction in this basic block, okay, up to the end of this basic block, as well as the last instruction in this basic block and up to the end of the basic block, but also up to this particular instruction. So essentially you see here, S2 is live from here to here, S2 is live from here to there, and irrespective of which which basic block you have executed, S2 is also live in basic block B4, right? So this is how you define these live variables. There are also other definitions that people talk about, but let's stick with this particular definition, right? When we say that this is a hole, it essentially means that in this region, I can actually use this register which is allocated to S1 to some other variable. For example, if there is a variable S3, I can actually, allocate the same register to S3 as well, because that is non-conflicting, provided S3 does not conflict over here, right? That's essentially what it is. So these are live ranges, and live ranges can have holes because the basic blocks are going to be arranged in your program, right, in some order. Either it is B2 followed by B3 or B3 followed by B2, but whatever order in which you arrange them, there is going to be, in some cases, there are going to be holes. So live range need not necessarily have to be contiguous. There could be holes, right? I'll give you one last example before we close, right? Here is another example where the S1 variable, right, has a last use over here, right? And S1 is not being used in this basic block at all. Now, how would this live range look like, right? So okay, we'll come to this conflict question a little later on. Okay, now let's ask the question, is S1 live here in the place that I have indicated? Obviously, S1 is live here because it is being used here. And also there is a subsequent use of S1 anywhere over here, and there is no redefinition of S1. Therefore, you can see that in this basic block and in any of these program points in this basic block, S1 is obviously live and S1 is live up to this particular point. But what about in basic block B3? In basic block B3, right, S1 is not being used. But that doesn't mean I can destroy the value of S1, because if the control flows like this definition of S1 and whatever value that was assigned to S1 is going to be used subsequently in basic block B4, and therefore S1 is kind of live here. Even though it is not being used, it is live. It is actually live through this basic block B3, correct? Therefore, when you define the liveness of the variable S1, it is not that it is only live in basic block B1 and B2 up to here, and then only live in basic block B4. It is in fact live throughout, because in basic block B2 also, even though it is not being used, it is contiguously live. So in this case, the live range of variable S1 is from this definition point and all the way up to this last use point, assuming that this is the last use, and it is in fact live through basic block S2. Because it is live through basic block S2, and this particular variable, right, which we were talking about, is defined over here and its last use is over here, right, that's live range is over there. My question was, can S1 and S2 share the same register? The answer is no, because S2 is actually live through the basic block, even though it is never used in here. Therefore, they conflict with each other, and therefore they cannot use the same register.